Do you have an idea for a new device that you want to produce and maybe sell? Do you want to introduce a new functionality in your smart home? Are you considering understanding how IoT works with a project that we can work with from beginning to end? Are you a microcontroller aficionado that wants to understand some new alternatives on how to write the firmware for those devices? Well, if the answer to any of these questions is yes, then good news, everyone. We're going to present this new series of episodes talking about IoT, microcontrollers, and pushing time series data to the cloud. During the last years, I have implemented quite a few automations using third-party software and hardware. This is a lot of fun, and I must admit that only in some cases improves the environment my family and I live in. This used to be much harder in the past, but nowadays the tools and their compatibility has improved a lot. You can do very easily automations such as switching the garden lights on sunset and then switching them off again at the approximate time that you want to go to bed. But you can go much further using your imagination. I have a door sensor on my garage door. When the door opens, the sensor triggers a timer. And if after 10 minutes the door is still open, then a red light turns on, letting me know that the door is still open and I may have forgotten to close it. That has helped me countless times to avoid having the door open involuntarily. All the joy and frustration that this brings me, together with some crazy ideas about things that I would like to create and even build, has pushed me to take a step forward and accept a challenge. And I was thinking about a new project, IoT project, that I could share with you. So I came up with an idea that I thought it would be suitable for writing the code, creating each of the parts, and even writing the software behind it. Let me introduce you to the requirements of this project. The idea is to have something that a startup could do, or at least close enough. So I will share with you the mission and the vision of this startup, together with, what is more important for this case, the first product. You don't have to buy the idea behind the product. I mean, there's no need to have a feasible business plan. We only are interested in the technical process behind it. The idea is going to involve more than one microcontroller unit. Most likely I will have a few and distributed among several rooms. And because the plan is to have them distributed, sending the data through wires is not very appealing. So I rather go with some traditional communications over radio frequencies like Wi-Fi or Bluetooth. If you are interested in learning with me how this would be done with other standards like Zigbee or Thread, let me know in your comments about this project. I might consider doing an addition to this series in the future. And the data that we're going to produce in these sensors is going to be collected by some computer. The computer will be local, and we will then push the data to the cloud, to a MongoDB Atlas cluster, where we will be using some of its IoT capabilities, such as time series or even charts. And finally, regarding the languages that I'm going to use, well, some of them are going to be on the edge or even out of my comfort zone. So please be forgiving. But my point is that this shouldn't be the limitation for creating such a project. The vision of our startup is that we need working environments that help us being more productive. And we believe that we can use technology, and specifically IoT, to help us with that. Our mission is to create, sell, and support products that will help us be more productive and feel more comfortable in our working spaces. And the first product that we are going to produce is a series of sensors that will measure the noise at the workplace and will help us control it better. I see the relief in your faces. We are not going to be talking about temperature sensors again. I have an instance of a MongoDB Atlas cluster that is going to be running on the cloud. And this is the instance that we will be using for uploading the data in the end. But first, I'm going to start by adding some sensors that I'm going to draw here as ears. So I will have one sensor here. I will add another sensor that is going to be here, and a third one that I plan to do here, and a couple more. So this is going to be here, and this final one is going to be here. For each of the sensors, I'm going to try to collect data, and I'm going to do it in a collecting station. So I'm going to use another symbol for the collecting station, which is going to be this inbox, but in the end it's going to be a Raspberry Pi computer, which we'll use in order to implement either the BLE Central or the MQTT client that subscribes to the data that is posted by all of the sensors. So each of the sensors is going to be connected with the collecting station. Let me change the drawing a little bit. So let's make it 10. Let's make it blue because this is going to be Bluetooth or Raspberry or MQTT using TCP/IP. Same thing was going to happen for the second sensor. So this will be here, third sensor, also talking to this one, fourth sensor, and finally fifth sensor that is also going to be here. So we have 5 sensors, but it could be 3 or it could be many more that are going to be talking to the collection station, and we will also want the collecting station, once it has the data, to use the MongoDB C++ driver in order to upload the data to the MongoDB Atlas cluster. In this case, I'm going to change the color of this connection. I'm going to use green, and I'm not going to make it dotted but solid. And we will be using TCP/IP with, as I said before, the MongoDB C++ driver. So this is it. This is what we plan to build, and this is what, let me have it like that, what we are going to build episode after episode in this series. So now that you are on board on this startup, let's go with the rules of engagement. As I mentioned before, my goal is not to do something with a single microcontroller unit. There are plenty of projects, some of them amazing, that do that work with a microcontroller doing something. So I think that my contribution would be worthless. Instead, my goal is to work in the different relevant aspects of this IoT project. That means that we will be coding firmware, that we will be taking care of the communications, that we will be ingesting the data, and we will be working with the data once it is in the database. With that in mind, it is important to know that my plan is not to spend too long doing this project. So I'm going to share the plan with you, and I am going to go step by step. But if one of the steps becomes too complex for me, or is taking too long, I may switch gears and I will go to a different approach. So if you still believe that any of the steps that I have skipped is still relevant, and you have some insight on how to make it easier or better, share them. Everybody will benefit from that, and I might add some content at the end of this project. I plan to use different programming languages in this project. I consider myself quite fluent in some of those, like Rust or Go, but it has been a long while since the last time I committed anything on a production branch for a real-world project for others, like a C++ or Python. So please be forgiving. My plan is to learn with you, and if you have any comments on how I can make it better, I would love to learn from them. A word on the tools too. My friends and colleagues know me as an Emacs user and fan, but I understand that some of you may have different preferred editors. That's perfectly fine. Everybody has his right to be wrong. Still, I want this to be useful to everybody, so I decided to use Visual Studio Code as the main editing tool here, as I did for the previous Rust videos. So please forgive my mistakes when using the tool, and I'm glad to learn from you again if you have any suggestions. And finally, there are some things that I don't plan to do within this project. Some of them because I don't know how to do them, and some of them because I want the project to be constrained in time and extension. The most of these ones are I'm not going to be creating any custom PCBs for the devices that I want to produce, and I won't be producing any 3D case for any of them. But most importantly, I won't be developing the firmware for each and every one of the device kits that I have shown you. I will implement some things for some of the devices. As we lazy people like to say, the rest is left as an exercise to the reader. Coming back to the goal of this project, it is to mimic what one would have to do in order to create a proof of concept of a new device from scratch. So I will start by selecting some microcontroller units that have device kits available in the market. This is the first step that I'm going to do, and it is going to be included in this episode. One of the main features that I want to have implemented in this project is wireless communications. The sensors will have to communicate wirelessly with the collecting station. So I have selected two alternatives to do so. The first one is to use BLE, Bluetooth Low Energy. Second one is to use MQTT over Wi-Fi. I will explain them in more detail when we get to the corresponding episodes, but initially it seems to be the case that BLE is more efficient in terms of energy consumption. However, there seems to be less complete documentation on how to implement BLE with MicroPython, for example. So we will explore both alternatives and we will choose one over the other. That said, my second step will be implementing the BLE peripheral for the microcontroller unit, and my third step will be to do the BLE central for a Raspberry Pi. I will continue by implementing the Wi-Fi counterparts. Step 4 will be to let the sensors publish their data through MQTT, and the step 5 is going to have the Raspberry Pi subscribe to the MQTT broker in order to receive the data from the sensors. Eventually, in step 6, I will use the MongoDB C++ driver in order to push the data into the MongoDB Atlas cluster. I have a couple of ideas that I might add at the end of this project, but these steps cover most of the things that I want to do for the project, so I will start with them and I may add some content at the end. If you have ideas for content that I can include here or enhancements on the one that I have created, send them to me. I will start this hands-on part by defining some of the features that I plan to use with these microcontroller unit boards. Then I will come up with a selection of affordable and popular boards that are available in the market. This is nothing like a top developer kits boards of this year, not at all, but rather this is going to be a list of suggested boards that you can choose to use to implement a project like this one. Let's start with the requirements for these developer kits. They have to implement at least one of the two radio frequency communication standards. So they have to support either Bluetooth Low Energy or Wi-Fi. They have to have a microphone on board that I can read from, or at least provide some free pins that I can use to connect an external microphone to it. It is important, or it would be helpful to have another sensor on board that will simplify the fact of gathering data from this board. It is not required, but it would make our lives easier. So having something like a temperature sensor that are trivial to read would be very helpful. Then we can switch later on to read the noise data and process it. I plan to have independent sensors, so it would be nice if I can connect a battery to them. Again, nice, but not required. And last but not least, having documentation available, having a community of developers behind the board that shares examples is something that is going to make our lives much, much easier. The first board is the Raspberry Pi Pico. It is created by the same company that produces the famous Raspberry Pi single-board computers. But in this case, this is a developer kit for a microcontroller unit, its own RP2040. The RP2040 is a dual-core ARM Cortex M0 Plus processor. The W variant of the developer kit board includes a chip that is able to do 802.11n Wi-Fi and 5.2 Bluetooth. It doesn't include a microphone in the board, but it has a temperature sensor. And there are several examples on how to connect a microphone to the board. It also doesn't have a connection for the battery. In order to write code for the Raspberry Pi Pico, there are several options. First one would be to use MicroPython. MicroPython is an implementation of Python 3 for microcontrollers. It is an efficient environment, and it offers all the niceties of the Python language. It is easy to learn, it has a mature environment, and it even offers you a REPL. We could also use C or C++ that are a lower level interface to the board that allow you to extract every bit of use that the board can offer you. There is also a JavaScript implementation. The concept is very similar to the MicroPython one. This is less mature, it is quite young, but the idea would be the same. You introduce the firmware there and you add JavaScript, that is a very popular language, code in order to work with it. And finally, there are some Rust crates that allow you to have a hardware abstraction layer to the board, but some additional effort might be required in order to use BLE or Wi-Fi, and probably use some additional crates like the Embassy family. The BCC microbit board was created for learning purposes. It includes many sensors on board, such as a microphone. It even has LEDs that we can use to get feedback when we're reading from the microphone. It uses a Nordic NRF 52833 that features a Cortex M4 processor. It comes with a full Bluetooth stack, but no Wi-Fi. And it has a socket to connect a battery. The educational purpose of this board is still present when we search for alternatives to write code for it. The most obvious one would be to use Microsoft MakeCode, which is a free platform to learn how to code using a graphical user interface, similar to Scratch, if you have ever used something similar to that. Another alternative would be using MicroPython, like we were mentioning for the previous board. But in this case, you have the MicroPython firmware and also the ability to write MicroPython from their own web interface. You can also use C++ using the Arduino IDE environment. And finally, you can use Rust, so much so that this is the example for the introductory guide for embedded Rust. So there's no better board to learn that. Still, BLE is not in the guide, but there are crates that would allow you to use the NRF soft device to create an implementation of BLE. The Adafruit Circuit Playground Bluefruit is aimed at people who have their first contact with electronics. It comes with a bunch of sensors, including temperature and a microphone, and it also has a very nice set of LEDs. Its main chip is a Nordic NRF 52840, and it supports full Bluetooth but no Wi-Fi. It comes with a socket to connect a battery on board, which is again helpful. We can use Microsoft MakeCode with this board, but its preferred environment is CircuitPython. CircuitPython is a fork of MicroPython, which comes with some more libraries and more refined ones, particularly for Adafruit products like this one. We can also use Rust. There is a crate for an older version of this board, and there's no BLE support, but again, we can use the Embassy crates in order to add this feature. Adafruit Feather is a platform that provides consistency among many different chipsets, so you can connect them to any of the Feather wings. That means any of the companion boards designed for this Feather platform. This board, the Adafruit Feather NRF 52840 sense, comes with the same chipset as the Playground one, so the NRF 52840, and it also has full Bluetooth support, but no Wi-Fi. It comes with many sensors on board, including a microphone and a temperature sensor, and it also has LEDs, a very nice RGB LED, and a JST PH socket that you can use for connecting a LiPo battery and even for charging it. While this board can also be used for learning, I would argue that it is more aimed at prototyping devices than the Playground one. So the environments are a little bit more complete. You can have CircuitPython as in the previous one, and as with all the Adafruit boards. You can have C++ using the Arduino IDE, and you can use Rust again using the previously mentioned crates. In contrast with all the ARM boards that I have introduced before, the Espressif ESP32 C6 DevKit C1 features a RISC-V processor, and a room module that provides not only Bluetooth and Wi-Fi, but also Zigbee and Thread communications, which are IoT-specific protocols for radio frequency. It comes with no sensors on board, but it does have two USB-C connectors, one that is meant just for power, and the other that can also offer you communications. Expressive boards have traditionally been programmed in C, C++, but during the last year or so, Expressive has been promoting Rust as a supported language for their boards. So there is even an introductory book that you can use that explains the basics of using this board with it. In this video, I have shared with you the project that I plan to develop with you in the next episodes. It's going to be a series of sensors that are going to be collecting noise data and sending it via either Bluetooth Low Energy or MQTT over Wi-Fi to a bespoke collecting station that we are going to develop. The collecting station will use the MongoDB C++ driver in order to upload the data to a MongoDB Atlas cloud cluster in the cloud, and there we will use some potential uses of this data. I have also presented you with a list of requirements for the boards that we will need to develop the project, and a preliminary list of boards that can fulfill these requirements. In the next episode, we will be coding the BLE peripheral in at least one of the developer kits. So get them ready and let's meet there.